All right, Chem fam, we're going to start with number 4 of our empirical formula problems. We've got butyric acid gets its name from the Latin butyrum, meaning butter, and it's a compound in rancid butter that gives it its terrible smell. Well, that is fantastic to know. Now, if we have a 2.5 gram sample of butyric acid, it is found to consist of 1.36 grams of carbon, 0.23 grams of hydrogen, and 0.91 grams of oxygen. So even though it's a 2.5 gram sample, since we have a certain amount of grams of each, we can use that for our actual grams. So there's 1.36 grams of carbon, there's 0.23 grams of hydrogen, and 0.91 grams of oxygen. As we know, the first thing we want to do is convert this into moles so that we can get a ratio between them. Remember, we're going to always divide by the molar mass because we're going from mass to moles. So if you use your mole map, you'll be able to do that. So I'm just going to fill in all my work here. 1 mole of hydrogen, 1 mole of oxygen, and I'm going to start putting in my molar masses from the periodic table. To do that, we know carbon is about 12.01, hydrogen is 1.01, and oxygen is about 16 grams. All right, I'm going to rock that out really quick and change my pen color. Remember, grams of carbon will cancel, and you'll be left with moles of carbon. All right, and that answer ends up coming to about 0.1132 moles of carbon. All right, if I do grams of hydrogen, they cancel out, and I end up taking 0.23 divided by 1.01 grams, and I end up with moles of hydrogen as my units, and my answer ends up being about 0.2277 moles of hydrogen. Okay, and the last one, grams of oxygen cancel out, units of moles of oxygen are what I'm looking for, and 0.91 divided by 16 ends up being about 0.0568 moles of oxygen. All right, do you remember what the next step is? Now that we have our moles, we want to divide by the smallest moles for everybody, okay, which is 0.0568. So let's divide everybody by 0.0568. What that is going to do is hopefully give us close to whole number ratios of each kind. So if you take these guys and divide them, you end up getting a number that's rounded and very close to 2. If you take and divide these guys, this ends up being a number very close to 4. And if you take and divide these guys, they go in evenly to each other, so that's a 1. So that ends up being 2 carbon for every 4 hydrogen for every 1 oxygen, or C2H4O. That would be the empirical formula. Now that might not be the molecular formula, remember. The molecular formula would mean potentially that, everything is double. Maybe it's C4H8O2. I don't know. The empirical formula is the lowest whole number ratio of all the atoms. But we did get a good head start on figuring out closer to what this thing is and what its empirical formula is. All right? So there's your answer right there. If we take a look at number 5, it says 3.927 grams of glycerine is found to contain 1.536 grams of carbon, 0.345 grams of hydrogen, and then the rest is oxygen. Okay, well, let's write down what we're given, right? Easy peasy, it's given to us already. So we have 1.536 grams of carbon, about 0.345 grams of hydrogen, and of course the rest is oxygen, so we just take the total, which is 3.927, and subtract 1.536 and subtract 0.345 grams, and when you throw that in your calculator, the amount you end up getting is about 2.046 grams of oxygen. So 2.046 grams of oxygen. All right, now that we have our grams, you remember what to do? Step 1, get them converted into moles. So we should be flying through that. We know that 1 mole of carbon goes on top. 1 mole of hydrogen goes on top. 1 mole of oxygen goes on top. Grams of carbon goes on the bottom. Grams of hydrogen go on the bottom. And grams of oxygen go on the bottom. Let's put in our molar masses. That's the mass from the periodic table. Carbons are always 12.01. Hydrogens are always 1.01. And oxygen is always 16 grams. Right? Remember, the reason this works is because grams of carbon cancel, grams of hydrogen cancel, grams of oxygen cancel, and you're left with the units of moles for all of them. All right, so let's quickly take the masses and divide by their molar mass, and we can get our answers. Okay, so 1.536 divided by 12.01 ends up getting us about 0.128 moles of carbon. If we take 0.345 grams divided by 1.01, we end up getting about 0.342 moles of hydrogen. And if we take about 2.046 divided by 16, we end up getting about 0.128 moles of oxygen. All right, think about it. What is the next step? Now that we have mole and moles, divide by the smallest mole. And for both of them, that ends up being 0.128 for 2 of the 3. So I'm going to divide by 0.128 to all of them. Why? Because I'm trying to find a ratio between them. This one ends up being 1. When you divide these guys, the hydrogen ends up being about 2.67, which isn't a very nice number at first, but we'll figure that out, okay? And then dividing these guys ends up getting 1. Okay, so 2.67 is not the prettiest number, but if we take 2.67 and we multiply it by 2, yuck, it doesn't give us a number that's very close to a whole number. If we take 2.67 and multiply it by 3, however, we actually get pretty darn close to a whole number. It gets very close to 8. So, since that is the case, we will multiply all these by 3. Why? Because again, since 2.67 was such an ugly number, we need to multiply it so that it's very close to a whole number. The lowest number to multiply it by that gets it close to a whole number is 3, and then it becomes very close to 8. 1 times 3 becomes 3, and 1 carbon times 3 becomes 3. So that means for our answer, there's 3 carbon for every 8 hydrogen for every 3 oxygen. So that becomes our empirical formula. All right, that was definitely a tougher one. That 2.67 didn't come out to something very close to a whole number, and it wasn't like 2.5 where it was obvious to double, but sometimes you have to do that. You multiply it by 2, then 3, then 4, then 5, until you get really close to a whole number. In this case, it was just multiplying by 3 that got you really close to a whole number. All right? How would you know that until you got some examples? Exactly. That's why we're doing this. We're learning as we go. All right, nice job on that one. All right, for our last example, it says a student extracted the citric acid from an orange and decomposed the acid. Her sample contained 1.875 grams of carbon. All right, I better write that down. 1.875 grams of carbon. It contained 2.965 grams of oxygen. Boom, boom. And it contained 0.210 grams of hydrogen. Let me throw my 0 in there. Okay, so now that we have all that information, let's rock it out. We have grams, and since we're trying to find the empirical formula, we of course want to get it into moles. So there's going to be 1 mole of carbon on top, 1 mole of oxygen on top, and 1 mole of hydrogen on top. I'm now going to divide each of them because I'm going from mass to moles. On the mole map, it would be divide by molar mass. So that's for carbon, 12.01 grams for carbon. Oxygen is always 16 grams of oxygen per mole, and hydrogen is always 1.01 grams of hydrogen. All right? If I do the math on that, and we've walked through this many times, but grams of oxygen or grams of carbon cancel, grams of oxygen cancel, grams of hydrogen cancel, and you're left with the units you're looking for, which is moles. All right, so the first one here, 1.875 divided by 12.01 ends up getting you about 0.156. 2.965 divided by 16 right here ends up getting you about 0.185. And 0.210 divided by 1.01 gets you about 0.208. All right, so these are moles of each of them, moles of carbon, moles of oxygen, and moles of hydrogen. All right, you know what to do now, I hope. Since we have them all in moles, let's divide them by the smallest amount of moles, which is 0.156. All right, so let's divide them. 0.156, 0.156 divided by 0.156. Yikes. What are these numbers going to come out as? Hopefully something nice. This one divided is easy. That's just 1 because it's the same number. 0.185 divided by 0.156, ends up being about 1.19 oxygens. Oh, that is not pretty. Okay. And then 0.208 divided by 0.56 ends up being about 1.33 hydrogens. Wow, that does not look pretty either. Okay, so we have to figure out some number to multiply all these guys by so that they end up being very close, all three of them, to a whole number. Now carbon's easy, no-brainer. Since it's a 1, no matter what you multiply it by, it's going to be near a whole number. All right, because it is 1 already. But this 1.19 and 1.33 ends up being a tough one. So if I double them both, they don't turn out to look very pretty. If I triple them both, they don't turn out to look pretty. Hydrogen would, but unfortunately oxygen would not. If I multiply by 4, it's not pretty. If I multiply by 5, it's not pretty. If I multiply by 6, they all get pretty darn close to a whole number. And so that's the one I ended up doing. So 1 times 6 carbon is 6 carbon. 6 times 1.19 oxygen is very close to 7. Okay? And then my hydrogen, 1.33 times 6 of them gets very close to 8. 8 hydrogen. Okay? So C6O7H8. And technically, not that you would really know this right off the bat, you would actually write it as C6H8O7, though I wouldn't take off if you did it the other way. But you put the hydrogen before the oxygen. Something we don't really need to get into right now, but the idea is that you're looking for ratios. Okay? Now that you've done that, try 7 on your own and see how well you do. But thanks for listening, thanks for following along, and we will get better and better as we practice more and more. Take care.